In this video, we're going to look at finding the average value of a given function over some interval. Okay, so let's talk about this concept of average value. Normally, whenever someone asks you to compute an average, right, what we've kind of learned as a standard method of practice is to add the things up and then divide by the number of how many they are. So let's say we're taking the average of 3 test grades over the semester. If we made a 73, an 84, and a 82, okay, we're going to add those numbers together and then divide them by 3, and that'll give us our test average for that semester, right? That goes into calculating part of our grade, right? And so what this method of calculating the average does for us, or is used for, is it's used for values that are called discrete, and they're used for a countably many number of elements, which in other words means finite. So what a finite number of elements means is that we can count them. So like we had 3. Countable number, right? And then discrete means we were just dealing with the numbers that we gave as our test grades, right? We weren't dealing with all the values in between those test grades. So we weren't dealing with like 79.76 and 74.82, right? We were just dealing with those 3 whole numbers that we had. So that's what it means by discrete. So looking at this concept of average value of a function over an interval, this idea is somewhat going to persist, but it's going to be changed quite a bit, because when we deal with average values of a function over an interval, even if we're over an interval just as small as we think it is of 2 to 6, we have to think about all the numbers that are in between 2 and 6, right? There's a lot of numbers sitting inside of there, including 2, 6, 3, 4, and 5, right? There's a lot of numbers in between each of those numbers, and even more in between all the different spans, right? So what we're going to do is we're going to tweak this notion of an average formula slightly to deal with values that are called continuous, which is what we're going to have. We're going to have all the values from 2 to 6, right? So we want everything, so it's a continuous set of numbers, right? So it's not discrete, it's continuous. It's all the numbers in between it that we want to take. And then we're also going to deal with, it's not really a countably many number of elements, right? It's not going to be a finite number. What we're going to need to deal with is we're going to something that's more of like an infinite number of elements in between these two numbers. Okay, so how we're going to do that is we're going to look at the definition of a function's average value that's given to us in the textbook, and you may have seen it in class. Okay, so we have f sub average, f sub ave equals 1 over b minus a times the integral from a to b of f of x dx. Okay, so let's do some substitutions with the values that we have here. Like we have f of x is here, and then we have a and b here, right? So let's substitute in these things so we can kind of condense down what we're dealing with. So here we're going to have 1 over 6 minus 2, which evaluates to 4, right? And that's times the integral from 2 to 6 of negative 5x minus 4. So now our function's average value is given to us by this thing, right? And actually, before I say this thing, I got to make sure that we include the dx. Okay, so now what we have is we have 1/4 times this integral is going to give us our function's average value. But then what we've come across so far in our class is that when we deal with a definite integral, or an integral that has bounds on it, right? So if we're taking the integral from 2 to 6, well, we're going to translate our integral into this thing that we have inside of here, and almost this like rounded triangle that I drew kind of right there. What we're going to end up doing is we're going to look at how this negative 5x minus 4 looks as it's graphed on a coordinate plane, and then we're going to kind of cut the function from 2 to 6 on this interval and look at what shape it makes. And we're going to use that shape to calculate the area, right? Because remember how we talked about a definite integral gives us the area under some curve? And in this case, it's not really going to be the area under a curve. It's going to be the area above a curve, because it's going to lie in the negative y part of the plane, just with how the function is notated. So we're going to look at the area above the curve from 2 to 6 that's in between this curve and the x-axis, right? So it's going to be a little bit, but we commonly just kind of refer to it as area under a curve, just as kind of like a general way of speaking. So, like I said, what we're going to do is we're going to graph negative 5x minus 4 on an xy plane, and then we're going to chunk it from 2 to 6 and just kind of draw vertical lines at x equals 2 and x equals 6, look at what shape it makes, and see what area formula we can use to calculate the area, quote unquote, under this curve. So we've talked about what we need to do. Let's go ahead and do it. Let's scroll down here a little bit. We can keep our function in the window right there, and let's go ahead and graph this thing. Okay, So we're going to draw a big XY plane, and we're going to focus on just the negative aspect of it, largely. Okay, and the reason for that is because we have a slope of -5, and we're wanting to reach all the way over to the x value of 6, right? So we need to kind of think that we're going to be graphing for a little bit here. But we know that this is our y-intercept, and this is our slope, so let's go ahead and start plotting some points. This is -4, and so here what we're going to do is we need 1, 2, 3, 4, 5, 6. So here's 2, and here's 6. So we need to graph more parts of our line to figure out just exactly what our function is going to look like, right? So here we're going to use our slope of -5 to go down 5 over 1, and we're going to keep repeating that process. Down 5 over 1, 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5. We go over 1, 1, 2, 3, 4, 5. Hang with me here. We're just about done. 1, 2, 3, 4, 5. We go over 1. We got one more to do. 1, 2, 3, 4, 5. Extend it down a little bit. And then we're dealing with this stuff here. So now, let's go ahead and connect these dots and create our function. Or create the graph of our function, rather. There we go. That's not too bad. So we have something that looks like this. And like I said, we're solely going to focus on the interval 2 to 6, right? And let's pretend that's a straight line that should intersect where it should. And this one's going to be interesting too. Oh my gosh. Oh, that actually didn't work out too bad. Okay, so now we're focused on the interval from 2 to 6, right? That's the bounds of our definite integral. And here we have graphed our f of x equals -5x minus 4. So now let's focus on this shape that we have here. What we have is we have a side parallel to this side, and then we also have another set of sides, but they're not necessarily parallel. Do we recognize what type of shape this is? And if we tilt our head a little bit and look at it, we know that that's a trapezoid, right? So then who remembers the area formula for a trapezoid back from when you learned it, okay? And if you were willing to guess that we have 1/2 times the height times base 1 plus base 2, you'd be correct. So this is the area formula of the little area under the curve that we're going to have in between these two intervals. So what we have is we have that the area under the curve is given to us by this boundary, right? So we want all the things that are inside of here. But then what 2 and 6 give us are like endpoints of where we need to stop shading, where we need to stop finding the area, right? So we go all the way along this curve until we hit here, and then we want everything from this curve to the x-axis, and we see that that boundary that we make here makes a trapezoid. So then we ask ourselves, well, what's going to be our base 1 and base 2? Well, base 1 and base 2 are the measurements of the sides that are parallel. So what I mean by that is that since this and this side, since they're parallel, we can call this base 1 and base 2. You could flip around the order, base 2, base 1, doesn't really matter, so long as you denote the correct sides being the bases, right? So you need to take into account that those are the parallel sides. Those are our bases. And then our height is given to us by the x-axis, or the length of our interval here. So 6 to 2, and we know that our height is going to be 4, right? But then how can we find our base 1 and base 2? Well, just like we looked at last section with the left and right endpoint estimations, what we're going to kind of see here is that the length of this base is given to us by the function's value at 6, right? Because we start at 0 and we go all the way down here to where we find our function's value to be the length of this base. So base 1 is going to be f of 6, right? And then similarly, base 2 is going to be f of 2, okay? So then what we're going to have is we're going to plug 2 and 6 into our original function and figure out what those are. So here, this should have been a 5 times 2 minus 4, and this is going to equal -5 times 6 minus 4. Okay, so let's evaluate these, and we get -10 minus 4, or -14. So we get that is going to be -30 minus 4, or -34. All right, so we have base 1, we have base 2, and then we said our height is 4. So now that we have all of our measurements for our area of a trapezoid formula, let's think back to what we said we were going to do and why we set out to do that. We said that looking at our original average value of a function formula that we evaluated it to, we said that we need to figure out the area formula for this enclosed region to substitute that information in for our definite integral, right? Because we said that this definite integral gives us the area under the curve. And we found that the area is going to look like a trapezoid using this formula here. We're going to take this average value of a function formula that we simplified it to and substitute in our area of a trapezoid formula in for our definite integral. Okay, so what we're going to have down here is we're going to have that the function's average value is going to be given to us by 1/4 times the area of a trapezoid, right? Because we said we were going to substitute in for the definite integral. We weren't going to substitute in for the 1/4 as well. That still needs to be tagged onto there. But what we're going to have here is a fourth times this thing, right? And we figured out that that is going to be 1/2 times, so that our height was 4, because it's the distance between the two bases. And then we're going to add our two base measurements, which is -34 for one function value and -14 for another function value. It seems kind of weird to call base lengths like negative numbers, but we are dealing with function values. And when we deal with area under a curve, where it's actually area above a curve like this, we're actually going to get a negative average value. So this whole area of a trapezoid, we said side lengths can never be negative. As we grew up in grade school, it kind of feels a little off, but it's totally legit, right? Because our average function value is going to be something negative because we're dealing with all negative values in our interval, right? So it should seem a little bit confusing, but it's okay. We're going to be all right. So we're going to simplify this stuff and get that, well, we have 1/2 times 4, and that gives us 2, right? So we have 2 times -34 plus -14 gives us -48, right? So then if we do this multiplication, we have a fourth times -96, or a fourth times -96 gives us -24. So then this is our function's average value of the function that we were given on the interval that we were given. Okay? So let's do a little bit of a recap. What we did was we looked at the difference between average of discrete and finite number of terms and kind of compared that to find the average value of a bunch of terms that are like a continuous number of terms, right? So not just numbers, but everything in between the numbers. So we use the definition of the function's average value to compute what we have here, and then using our knowledge of definite integrals up to this point, we know that we can substitute in for our definite integral an area formula that kind of dictates what or that not dictates, but represents what the shape of our shaded region is going to take the form of here. And we found that to be the area of a trapezoid. So we found the dimensions that we needed, and then we plugged in for our definite integral the area of a trapezoid formula. We evaluated it to find our function's average value. Okay, so this is the process that we use up to this point right now for finding the average value of a function. The biggest thing to remember is this formula, and then after we graph it, we got to determine from there what shape our shaded region takes so that we know what to substitute in for our definite integral.